welcome.
Hello. Hope everyone is doing well. Welcome to episode 1 of Pine Research's YouTube live stream Q&A. We're your hosts. I'm Dr. Alex Peroff, and with me is Dr. Neil Spinner. We're very excited to be with you today. The goal of these live stream Q&As is to try to answer some of the questions, the many questions that you have given us during our webinars and YouTube videos, phone calls, emails, directly to us, things like that. And so today we're going to mostly be focusing on questions related to the potential window, EIS current range, 2 and 3 electrode systems, and then IR drop. So the format of this Q&A, again, about topics like potential window, EIS current range, 2 and 3 electrode systems. And while normally you might be able to answer these, with just a YouTube comment or talk a little bit about it in the webinar, our goal here is to really give more of a deep dive into some of these questions during the event. And so we're going to try to answer between 3 to 4 of these questions just from what people have asked us. And then we're opening it up to questions from the chat. So if you have questions in the chat, this would be, just ask them. Now, one thing to note also, if you're viewing this live stream after it has ended, I've added timestamps in the description so you can skip ahead to wherever you want to see or what questions you may have. Now, we are broadcasting on Zoom right now. And so there's about a 20-second delay or so between when we say something and when we see something in the chat. So just keep that in mind when answering questions and stuff.
We'll do our best to, give it a little bit of breathing time after we've talked about a question or something like that, to look for your questions if you have any, because of that delay. So we'll, like Alex said, we'll try to be aware of that. We also just want to give a a shout out and a thank you to those on YouTube who are our YouTube members. We launched our membership on YouTube not too long ago. We appreciate those who have joined. That's where you can find, for example, the archive of all of our previous webinars and some of this content as well. We're going to be doing more and more of this as time goes on, and we really appreciate your support. And we hope that everybody is happy to subscribe and join our YouTube content. And anyway, we appreciate it. As I said, or as Alex said, I should say, if you have questions, feel free to type them anytime. We'll try to get to those. We do have some prepared questions here that we hope you'll find interesting, and then we'll try to get to questions about those, and also just any questions that you have that are in general. Looks like there's been a couple already. Mm-hmm. We'll try to get to those, when we have time. I just wanted to sort of add a couple of things here before we get going. And generally that's, if you're joining us, we appreciate it. And we do know that electrochemistry is difficult. We kind of want this live stream event to be kind of like a safe environment, for people to feel like when you're asking questions that you might, maybe be embarrassed or anything like that. We just want this to, if you have a question, please feel free to answer it. If we have time, and frankly, if we know anything about it, we'll do our best to answer. And we want you to feel comfortable to ask, whatever questions that you might have about electrochemistry in general. We want to try to be here to help. We're going to aim for about an hour or so, but we could go longer if there are questions, if there's enough interest, and we'll do these as often as basically there is interest from you all. And we'll go from there. And then the last thing that I'll say is that Alex and I, in case it isn't obvious, are American. And so we are going to do our best to pronounce everybody's name, but we will likely get them wrong. So apologies in advance for when we mispronounce anybody's name. We're doing our best here. That's all I can say.
Thank you, Neil.
Yeah.
All right, so let me show you. We'll just kind of go through the list right now. We do see some questions in chat, but we will address them, I think, as we start to talk about things. So the first question is from Abdul Malik. Abdul Malik asks, how to determine the potential window for CV, cyclic voltammetry, for example, in the case of nickel oxide nanoparticles that are deposited on aluminum foil. So to determine the potential window for this specific system, I would need a little bit more information. But what I would like to tell you about is exactly what is the potential window, and then how you can determine the potential window for any electrochemical system. Okay, so let's start by just going to, let me just adjust my camera. I thought that was good. Okay, so let us start with talking a little bit about what the potential window is. The potential window is the available, basically, window or range of potentials that you can observe in a cyclic voltammetry experiment where you don't have any redox reactions occurring, right? And so you've probably seen something like this before, so if you have a cyclic voltammetry experiment, you have, your current as the y-axis, right? It's current. Actually, draw that a little bit better. You have the current as the y-axis, you have your voltage as the x-axis. And when you do a voltammetry experiment, you get something that looks a little bit like this. Kind of this flat region in the middle, bear with me. And then at the edges, you get this exponential increase in current. And then at lower potentials, you get this exponential decrease in current. And so the potential window is really this area in the middle where you get very little to no current, right? There are very few to no redox reactions that are occurring. So your analyte of interest is going to react in this area. Now, this curve should also look somewhat familiar if you've studied, Butler-Volmer kinetics. This is from the Butler-Volmer equation. Now, as you go, now, of course, there are some people who are actually interested in studying stuff like this, the stuff that happens outside of the potential window. Like in the case of water, this might be something like hydrogen evolution or oxygen evolution. But in this case, we're not interested in talking about these. We just want to look at what's happening from here to here, from this potential to this potential. This defines your potential window. All right. So the key to determining the potential window is you must do this experimentally. You can, and I'll go over a little bit later, the theoretical, like how you would theoretically think about this or theoretically come up with the potential window, but really you need to determine it experimentally. And to determine the potential window experimentally, you just need to do cyclic voltammetry experiments within a very short, narrow range, and then gradually increase. So maybe you start sweeping here, and it's like, okay, nothing's really happening. Something is sweeping maybe from here to here. Nothing's really happening. Okay. Here, also good. Maybe you start to see a little bit of the tail end of this exponential increase in current. But then when you go to like here, you're like, okay, maybe this is the potential window. This could also be another redox process. You don't know. So you may also need to test at a larger range, right? So you might want to keep doing this, keep successively creating these voltammograms. And it doesn't matter, what the scan rate is, but what is important is that you have the highest current range selected, or you use auto range. Some potentiostats have an auto ranging feature, because what would happen if you don't select the highest range, what will happen is as you're sweeping the voltammogram, so let's use blue instead. If you don't have the highest range selected, you'll get this overload error, and you'll just this flat line. And then you have no idea whether you're actually running into an issue or not. You'll also get this on the other side. So voltammogram will go, and then it'll flatline. So experimentally, set the potential, go back and forth, and set the highest current range or auto range on your potentiostat. Now, the reason why you need to do this all experimentally is because what determines the range, so let me just clear this. So there's several things that determine what is the potential range. It's the working electrode, counter electrode, reference, the solvent, the electrolyte. Every single thing inside of your electrochemical cell determines the potential range. And not only does every single thing determine the potential range, but the interactions between things determine the potential range. So how these all interact with one another governs the potential range. So for example, if I have water, H2O, water will decompose to form hydrogen gas or oxygen or oxygen. Depends on pH, depends on a bunch of other factors. And this tends to happen that has a suitable range between -1 volt to about +1 volt. But that's the general case. But this happens on a glassy carbon electrode. So if my working electrode is glassy carbon, that's what I get. But if I use something like a boron doped diamond, BDD sometimes is the acronym, you can actually have something higher. You can have like -1.2 volts to say +1.2 volts. That becomes your potential window. And then similarly, if I had a platinum working electrode, I actually have a smaller range. Maybe it's something like -0.5 to about +0.5 volts. So it's not just the solvent, it's how the solvent interacts with different working electrodes, different types of working electrodes. So you can't you can go through each iteration of what interacts with what, but the best thing to do is just to determine, okay, experimentally, let's just sweep the potential and slowly keep increasing the voltage range, keeping the current range super high, and that will be the best way to determine it. There is one last thing I want to mention, which is that, I'll use red here, is that potential windows can be described in two ways. There is what's known as bipolar and symmetric. And so bipolar means that it's accessible to both plus and minus. So you have minus voltage, plus voltage. That's bipolar. Symmetric refers to having both an equally spaced negative and positive voltage. So also water in this case, it's symmetric. But if I had something like copper, let's just do copper, for example. So a copper electrode, really in water has more of a range of say -0.2 to say -1.2. So in this case, copper would be polar. It only has accessibility to the negative voltage range, and it's asymmetric because I can only go from -2 to -1.2. It's not a symmetric evenness. So that's another thing to consider when you're looking at the potential window. But this is how you would go about determining the potential window for just about any electrochemical system. All right, so I hope that was helpful, and I'm going to stop sharing my screen. And if anybody has any questions about that, feel free to ask them in the chat. If you come up with a question later, we'll address it. But otherwise, we'll after all of our questions, we'll go through as many questions as we can that come up during the chat.
Yeah, excellent. Thanks so much, Alex.
Yeah.
I'm gonna get to the next one here. Let me bring up our question 2. So hope everybody can see here. We've got this next question was from Karen, and she asked, what is the lowest current you could measure accurately for EIS? And then asking, is microamps as a suggestion or part of the question here. So I'm going to try to answer this for you now. Okay, so let me share as well with a little whiteboard here. So first of all, the kind of differentiation I would make is between the two kinds of impedance that you can do essentially, right? Let me make sure that this is like a thick enough line. All right, perfect. So, right, essentially we're doing EIS. We have two options. We can do potentiostatic, right, or galvanostatic. Now, I'm going to save galvanostatic for a second that I'll kind of describe here. And the main reason is because it's actually an easier, more straightforward answer. But potentiostatic, it's a little bit trickier in some sense. The answer to what's the lowest current I can get or whatever, however you want to think about that. With potentiostatic, right, the fundamental experiment is that I send a sine wave of potential to my system, right, whatever my electrochemical system is here, and the output is a current. Galvanostatic, of course, is just the exact opposite. I send a current in to my system and my output is potential. Okay. So this is why hopefully you can kind of see it's more straightforward to think about what current can I use when I'm in galvanostatic mode, because I'm controlling the current. When I'm in potentiostatic mode, it's different because I'm measuring the current. And so there's a reactionary kind of thing going on here. Okay, so we're really more considering the potential that we input of our amplitude, right? Our amplitude sine wave for our E versus T curve for potentiostatic EIS, okay? And so when we're doing EIS, what we're usually observing is something like a cyclic voltammogram. Okay, so we usually have these E and I versus T, these sine waves, but when we view it, we have what's called a Lissajous plot. So if you've done impedance, you probably are perhaps somewhat familiar with this. And usually it gets something that looks like an oval or maybe like a line, depending on what your system is looking like, how much resistance, how much capacitance, et cetera. You'll get plots that look something like this. Now, the shape of the Lissajous and how it looks is kind of the indication of how much current do I need to be able to accurately measure. That's going to be sort of where that answer lies, okay? That's the first part of this. Now, the second part is that generally speaking, as I go from high frequency to low frequency, which is the order of an EIS experiment. We usually start at high frequency, we go to low frequency. Generally speaking, the impedance goes up as my frequency goes down. So if I think about Ohm's law, there's an analogous, you can think about it in terms of impedance, right? Z or R, right? I'm just drawing R for the most common way that you think of Ohm's law, V equals IR. Essentially, if I'm doing an impedance experiment, I'm picking whatever my amplitude is. So I'm setting my voltage, right? However many millivolts, 10 millivolts, 20 millivolts, whatever my amplitude is, right? Well, as the frequency goes down, R goes up. So as R goes up, if V is the same, I is going to go down. So this is another thing to be aware of. So when you're thinking about, well, how much current do I need to be able to get a good signal, to be able to measure something at all? You have to consider, okay, well, at the beginning of my experiment, I'm probably going to get a certain amount of amp, milliamp, microamp, whatever it is, response. And by the end of my experiment, that value is going to be lower because the impedance, the resistance is going to go up and my current response will be lower. So to a certain extent, you need to have a little bit of like planning in advance when you do impedance experiment potentiostatically, which sometimes requires trial and error because you don't always know what your current is or your impedance is going to be at the end. But sometimes this means that you want to be careful that your amplitude isn't so small that by the time you get to your low frequencies, you have such a small amount of current response because your impedance is so high that now your signal's poor. And so when I say your signal is poor, what I mean is that visually, your Lissajous plot might start to look, right? You should have a nice, great, nice, a smooth kind of a circle or something. But what you might start to see is that it looks jagged or pixelated or not tracing on itself. You know, that is an indication. You see some noise in your Lissajous, that could be an indication, you know, when you look at, well, what are my I and E? Well, I'm controlling my E, but what are the you know, currents that I'm seeing here? And now for a lot of potentiostats, and I'll just give this general kind of advice here, it of course is going to vary a lot depending on the system you're using, the potentiostat you're using, all that kind of stuff. But for like a typical 3-electrode system, let's just say aqueous or non-aqueous, you're looking at probably like sub microamp currents. You might start to see some of this kind of pixelated behavior. Like you probably, so microamps as a suggestion from this question was probably a decent, you know, guess, let's just say, because as you start getting smaller than microamps and, you know, nanoamps or whatever, smaller than that, you're hitting the limit of what the potentiostat can like measure accurately. And so what happens is the analysis from the potentiostat is actually done with something called FFT, fast Fourier transform, or DFT, discrete Fourier transform. But basically that's just a mathematical method for deconvoluting a sine wave, right? So when you have your sine wave, like these sine waves up here, right? The software deconvolutes this into an impedance, you know, magnitude and a phase angle. Okay, great. But if my you know, sine wave looks like this, well, then you have, you know, some crazy behavior. And so what happens is that when the FFT analyzes this right here, well, it gets some pretty bad results for Z and phase. And that's why your impedance data looks poor. It's because the analysis of this FFT can't really pick out a sine. It's not really even a sine wave after, you know, if the resolution is really bad. Okay, so that's kind of for potentiostatic, the gist of what's happening, what you're doing. And then, you know, the general, I don't know when you say like the general advice about it, you know, numerically, you might say microamps is a good place to think about if your response for a typical system is in the microamp range for whatever potential amplitude you pick. So you pick 5, you know, millivolts or something, and you're getting like 100 nanoamps. Well, you might want to increase it. Okay, great. I'm getting 10 microamps now when I do 20 millivolts. I'm just making up these numbers, of course. Oh, great. Well, that might be in the range that I'm looking for, because then let's say by the end, my impedance or my resistance has gone up. Okay, well, now I'm dropping to like 5 microamps instead of 10, but it's still enough. So great. So those are some of the things you want to think about. And then, you know, having a potentiostat and a software, if you can, that shows you the Lissajous plot live. Not some do and some don't. So when you have software that just sort of like shows you the Nyquist plot or the Bode plot showing up live, but not the Lissajous, you know, if your data looks poor, you don't know why. But if you can see the Lissajous plots when it's collecting the data live, well, you might be able to get an indication of what's going on, and that can be helpful. The second and last part of this, as I said previously, was with galvanostatic impedance. And the good news with galvanostatic impedance is that it's much more straightforward. So I'll answer this actually with our software. I'm going to share our software here. Hopefully you can see what I have is, hopefully if my battery isn't dead, I have a battery connected to potentiostat here. Okay, so you can hopefully see our software. I'll just run an OCP to hopefully convince myself that it's working. Yeah, I've got about 3.8 volts. So I've got a little tiny lithium ion battery coin cell connected to my potentiostat. You can see it's got a potential here. And so the answer, perhaps to try to be direct about this right now, with what's the current, you know, what's the best current to use or whatever for galvanostatic impedance? Well, typically galvanostatic impedance is done on things like batteries, fuel cells, things like that. A good rule of thumb is C over 100. Okay, so a battery has what's called a C rate. In this case, my battery has a capacity of 85 milliamp hours. It's a pretty small coin cell. Okay, so what that means is that it can, in theory, draw or be provided with 85 milliamps continuously for 1 hour, and then it will be fully charged or discharged. That's that's its capacity. So if I'm trying to get impedance on it, I'm going to do it galvanostatically. No set point. We're just going to kind of run this pretty quick here just to give you an example. It's 85 milliamp hours. So a good rule of thumb to start, as I said, C over 100. So that's 1/100th of that. So that's 0.85. 0.85 milliamps, that's where I can start for my amplitude. I'm just going to do a short little window of frequencies just to kind of get a quick first example. Okay, so we're going to run through these and you can hopefully see the Lissajous plots. And my hope is that they see it looks a little jagged. So this is what I was talking about before. It's like, okay, well, I could see my Lissajous plots and either getting a little smooth, but some of them look a little bit jagged. Maybe they're not quite tracing on themselves. My resolution might not be that high. You can see my potential is in microvolts, right? So in a sort of a opposite way, we're not talking about how much potential I need. You know, the question was related to current, but you can think about it in a similar way. Well, I should also have enough potential to get a good response. And I'm at less than a millivolt here. So I'm also pushing the limits of my potentiostat in some way. And, you know, it's not the greatest data. Hopefully I've tried to create data that looks bad on purpose here so I can kind of show you, right? So the point of this is to illustrate. Let me get my plot all kind of aligned here for you and zoom a little. So you can see that some of these points are, you know, not equally spaced well. There's a little bit jumping around. The reason that you do it this way, C over 100 is a decent place to start. The reason that you do that is because it's safer. Okay, so I don't run into as many like possible problems. Let's just say if I do less current, I'm just gonna have bad data. But I'm not like the worst would be if I did like, oh, I'm just gonna put like an amp in here. And I might over discharge my battery. I could damage it. So if I start smaller, I can always increase it. Similarly to how Alex talked about getting the potential window, you start in this narrow window and then you sort of progressively increase your potential window until you hit the oxygen evolution, hydrogen evolution, you know, of your Butler-Volmer like you drew. In the same way, here, I started at C over 100. Well, that doesn't seem like it was enough. I'm going to increase this. Let's just go to like 4. This is like C over 20, something like that, right? I'll run this one more time, and then this will be the end of this question for you. But you can see here that if I increase now, I've seen, okay, well, C over 100 was a little bit small, but it was a good place to start. It was clearly getting me data, but maybe not the cleanest data. So now I've increased my amplitude a little more. I'm going, you know, up or down 2-3 millivolts, something like that. That's not that much. I'm not going to be really overly charging or discharging my battery. It's probably still pretty safe. You know, if I were doing like 10, 50, 100 millivolts up and down, that would be a significant amount of charge and discharge. So that's why I'm moving this, you know, slowly and progressively in a trial and error kind of a process. And so this is a good example where, okay, now my data looks a little bit cleaner. And I did a really narrow range here. You can see it's still not maybe perfect, but doing Kramer's Kronig just to kind of check the validity of the impedance here. You can see previously with C over 100, you know, it looks okay, but my error is also pretty low. But when I do a better, slightly larger amplitude, my error is even lower. It's like an order of magnitude almost lower. And so that's just sort of that example there of a place to start for galvanostatic impedance, you know, what kind of things you can expect for an appropriate current. So the actual value of the currents depend on the capacity of your battery, of course. So you can't really say milliamp or microamp. In this case, it really depends on how big your battery is. But that's a place to think about, you know, what works, right, for EIS galvanostatically, let's just say.
All right, very good. So, so the next question we got was from Hamid, and this question is actually somewhat related to Luca's question in the chat. So I think I will very quickly go over Hamid's question and kind of segue into Luca's question from the chat about 3 electrode systems and beyond 3 electrode systems. So if you're okay with that, Neil.
Yeah, please go ahead.
We can answer that from the
It's
chat based
better
on
to
this.
integrate everything as we
Yeah.
go if we can. This is perfect. Yeah, thanks
Okay.
for the question, Luca. We appreciate it.
Yes. Yeah. Thank you, Luca. And thank you for being a member as well. So Hamid asks, he's learning electrochemistry kind of for the first time, and he wanted to know, why do we need to use a 3 electrode system instead of a 2 electrode system? Why is the reference electrode necessary? So let me kind of go, I can do this relatively quickly. But what we learn in chemistry classes, when you're first learning about electrochemistry in a Gen Chem class, is that you have an electrode. Let's just call this E1. And you have some kind of power source. And then you have your E2. I'm kind of drawing these out so that you can, so I can fit stuff in between it. All right, and then this here, this is your electrochemical cell. Okay. Now current, you use your power source to drive current between these 2 electrodes, right? So current is flowing. And when current flows in your electrochemical system, there's going to be maybe some kind of oxidation reaction, and there's going to be a reduction reaction. There always must maintain some kind of charge balance. Hamid's question is about whether or not 2 or 3 electrode systems are needed or necessary. And if all you want to do is just oxidize or reduce some species, then all you need is this 2 electrode system. You will actually need a 3 electrode system if this is the goal, which is just to generate some kind of species. But if I had a question, let's say I was interested in determining what is the potential where this redox reaction is occurring. Like what's the potential? Well, I could take a voltmeter and let's use blue. I could take a voltmeter off to the side. And then I could hook one end here to my E2 and one end over here to my E1. And I could measure the voltage. It's like a little dial meter here. So the voltage is changing. So I can measure the voltage difference, and maybe I get -5 volts, maybe I get -2 volts, something like that, maybe 0.3 volts, something like that. So I can measure the voltage difference between these 2. But these numbers are changing, especially as current flows and a reaction is occurring. These numbers are going to change, and maybe this becomes, -4.9. Oops. This -4.9, so 4.9 volts. So maybe that happens. But if I'm getting this change from -5 to -4.9, which side is causing it? Is it E1? Is it E2? Is it both? Because this is happening, stuff is happening, it's changing. Faradaic and non-Faradaic processes are occurring, but also Faradaic and non-Faradaic processes are occurring here. So you have this potential difference. And so because of this, we implement a reference electrode in a 3 electrode cell, which looks a little bit something like this. Some kind of wire in a glass tube with a frit and some solution. And instead of connecting one of my leads from my voltmeter there, I connect it to the reference electrode. And the reference electrode maintains a stable potential in my electrochemical cell. So while I have current flowing between E1 and E2, my potential is being measured between E1, and let's just call this ref. And so if I get this change from -5 volts to -4.9 volts, the potential of the reference is stable. So any change must be due to E1. And now I can start to understand the reactions and the thermodynamics of E1 independent of E2. So if I'm interested in more analytical information, more analytical stuff, then basically this is why a 3 electrode system is employed. Now, Luca's question is about what happens when you have more than 3 electrodes in your system. by using a multi-channel potentiostat. So, and if you're measuring OCP of multiple working electrodes in the same electrolyte, will the working electrodes interfere with one another? And for example, show, for example, all the same trend or drift, or will you measure the same OCP if you're working in independent solutions, right? So just kind of what I'm gonna guess visually is, let's use this. So there's a situation, and Luca, please write a comment if I'm doing this wrong or you need clarification. But you basically have some, a bunch of cells. You have a bunch of different, let's see, little like working electrodes, all in your electrochemical system, your electrochemical cell, and they're all tied to a common. Just going to use random colors. They're tied to a common counter, and they're tied to a common reference electrode. So this is just symbolic, at least right now. All right. So all this goes to your potentiostat. So this is your.
Yeah. The only thing I'll add here, I
Yeah.
guess, as we're talking through Luca's system here, Luca, you could clarify, and also anybody else that has some input. I guess it's like there's, you can correct me if I'm wrong, Alex. There's basically like two kinds of multi-channel or multi-systems. One is the way you've drawn it, where there's one reference, one counter, and a bunch of working. And then there's other ones where it's each working has its own referencing counter, right? So, I mean, so there's those two options, just to be clear, right? You can sort of have, you can have both options, I guess.
Yeah. Yeah.
So this is the easier to draw.
Yeah,
I'm not going to make you draw
draw
12 more counters and references in your thing here, but yeah.
And I think there are some people who do have like those 3 electrode systems in different ones where these are not all tied. And Luca can comment on whether that's the system he's working with. But my opinion is that, let's see, yes, this is exactly the setup. Also, do I really need to use the counter electrode during the OCP? So do I really need to use the counter electrode during OCP? I think you.
So the answer to that question is probably yes. And the reason is that, well, okay. So the options are do a 3 electrode setup, like here, like Alex has drawn. Right. And measure OCP and then do whatever other kinds of experiments you want to do.
Yeah.
Or measure OCP in a 2 electrode setup, but the 2 electrode, I mean, it's like a lot of 2 electrode. It's like multiple 2 electrode setups combined or something, right? Because you have a multi-stat. And to be honest, part of, I guess our answer here is a little bit of ignorance, because I don't know what system exactly you're using, like how exactly it work, like what the software, there's some unknowns here for us, like how is it like electronically coupled or working, right? So some of that's a little bit of unknown for us. So pardon our answers here, but you would have to connect like a 2 electrode setup, for example, with like working to reference. So it's like you can cut the counter out, but you need to make sure your reference is the reference, so you would have to basically have the counter electrode line. I guess it's tricky. So sometimes
there's a part of me that thinks Luca might be right, because the reference is just sensing. The counter would be the thing that would drive anything, and only for OCP.
This is exclusively. And again, some of this is my knowledge of like how like our company, like how Pine's potentiostats work. So for example, the way our company's potentiostats work is that when it's in OCP mode, it basically internally disconnects the counter electrode.
Yeah.
Right. It's like it's actually not connected like physically inside. I don't know if that's exactly how every other company's potentiostat does OCP, for example, but if it is, then in some sense you are correct that while doing OCP, you can have the counter connected or not, it doesn't matter.
Yeah.
But that's exclusively for OCP and not for everything else, right? You would need to have everything connected as soon as you start doing CV or bulk electrolysis or whatever you're doing.
Yeah. And I also think that, so the question, will the working electrodes interfere with one another? And So when you take any measurement, there's always a tiny bit of current that passes. It's tiny. It's super minimal. I think if you were to say that that's negligible, then I don't think the working electrodes would interfere with one another. They may or may not actually show the same drift or the same trends, like because they're literally positioned in different places, like because this is here and not here, its distance from the reference is different. And this is closer to something that's vibrating, so it feels something different. Like you're going to get little things like that that will show a different OCP, but
I mean,
it'll be pretty close, but different.
I think most likely the answer is practically probably not, that the working electrodes, in other words, I don't think the working electrodes will probably interfere with each other very much, but there, you know, what Alex has drawn here is actually a good indication of this. One possibility of how it might is that, and this actually leads really into my the last question I'm going to talk about, which is in response to IR compensation. So if you have an array of working electrodes, they're probably each a slightly different distance from the reference electrode. Now, the way Alex has drawn it, it's like the farthest one on the left is like, you know, spatially farther from the reference than the one on the right. You might have a situation where they're like, I don't know, like all four of them here, and then, you know, the one so they're all sort of equidistant, but basically the distance between each working individually and the reference will dictate the IR compensate, the IR drop or the ohmic loss for that one. And so that in that way, if you have some of your working electrodes that are farther from the reference, it could mean that some have a higher IR drop. And then as far as if your thought process is, do they interfere with each other because there's processes happening on the surface of one working electrode and it's physically close to another one? So if I'm like reducing or oxidizing something on one, is it like making its way to the other one to do a thing? That's a good question. And the answer to that is probably more rooted in how far away your working electrodes are in solution. So like the diffusion layer is microns, of some amount of microns, hundreds of microns, I don't know, maybe a millimeter at most, right? Like something like that. So I see you put another question, but I'll just finish this thought and then we can sort of look at that. But basically something like if the working electrodes are like, you know, you have like interdigitated arrays and they're like super close, and it's possible you could have effects, I think, like between them. But in many cases, if they're like spaced a little bit away from each other, you know, and the electrodes are usually pretty small in this case, it's like, it's unlikely that each working electrode is going to be able to like generate enough stuff to severely impact its neighbor. Yeah. That's at least a millimeter or 2 or 3 or 4, we know, however far apart it is. It's like the diffusion, whatever's going on at one is just not likely to be impacted by another.
Yeah. Now the only thing, here's the thing that could change things a little bit, which is electronically, how are the working electrodes wired electronically? This is something you could not know unless because ideally each working electrode should be isolated from one another, but like electronically, some of those wires may be connected or they may sense a little bit from each other.
Yeah. Like, is it multiplexed or is it you know, exactly how it's wired is I have no idea. Yeah.
It's small. Like that shouldn't really make a difference, but sometimes there are strange things that happen where it's like, oh, these electrodes actually are kind of cross coupled in a way on the electronic side of the potentiostat. So yeah, but I hope the sense. Also, Neil, do you want to draw something? Because I can also stop sharing.
Well, I'm such a good artist, so I probably should, but
and you'll need to share later. So
yeah,
I'm gonna stop.
Yeah, that's okay. I think, I mean,
this answers Luca's question.
My hunch to your last question, Luca, is, you know, your doubt about interference, which is a reasonable thing to be concerned about. I would say they're all in the same electrolyte, and so, you know, there is some. Yeah, I mean, technically, there's some ionic connection. Like they're all in the same electrolyte bath, and so you have some sort of ion bridge between all of them. But I don't suspect that would impact the behavior very much, because you know, that ion bridge, you know, is effectively needed to balance charge for the potentiostats perspective between like working and reference electrode. And so as long as that's maintained, I don't think you'd have much of a problem, to be honest. The only other things, like we said, we talked about the distance between them. As long as it's like somewhat moderate, it's probably not going to impact one. Electrochemistry is such a surface science. It's so surface specific, right? It's like what's happening on one surface is unlikely to like impact what's happening in the bulk or too far away or anything like that. So it's not likely that you have these impacts from something really far away. And I'm talking about a few millimeters is far for electrochemistry, right? The only other possible thing that could happen, and again, this still leads more into my next question, which I'm sort of giving away half of it here, but it's that if your counter electrode doesn't have a large enough surface area, you could have problems too. If they're all working at the same time, like the combined surface area of your working electrode is like X, times however many working electrodes you have, you could have some situation where the counter electrode is being used as the dump for all of them at the same time. And then the surface areas start to, be comparable. Like, I don't know, you could have a compliance voltage issue or something like that. So I mean, that could happen. But again, a lot of this is like rooted in how is the electronics of your system. Like there's some other unknowns there.
Yeah.
Right?
Yeah, I think so. One thing I always like to do with all types of kind of questions like this is you can take, while you're running OCP, you can take a digital multimeter and just hook up one lead to the one working electrode, another lead to the reference. And then just kind of, working. Is it changing? Disconnect this one.
Yeah.
Oh, is this changing?
Yeah. So you're running a thing like CV or on one electrode one, simultaneously measure the voltage of its neighbor with a voltmeter and see if it's changing. And if it is, if you see a distinct like spike in current, potential, whatever, while the other one's running, that's also a good experimental way to like say, oh, well, it's obviously impacting and why or how. Is it a solution thing? Is it an electronic thing? I mean, I don't know the answer to that, but you'd at least get an answer. Whereas if you see its open circuit potential is not changing, it's pretty steady, then that would also be an indication like, hey, it's not, which is good, right? You don't want it to, in theory, interfere.
Yeah.
I hope that answers that question
answers
somewhat adequately, I suppose. But keep the questions coming if you do have any more. I'm going to answer the last prepared question we have here, and then we will be happy to address any other stuff that pops up in the chat here on YouTube. But the last question is sort of a combined one. I've gotten a handful of questions or just sort of comments of this nature. As I said, it's basically about IR compensation, ohmic drop. And could I, to explain about ohmic drop, the first part of this being, can it be calculated from the resistance in a Nyquist plot? What happens, what does it mean if you have a high R value, high ohmic drop, and then does the distance between working reference counter, how do those physical distances? So again, I just kind of covered some of that with your question here, but how does that impact impedance results, and in particular the IR drop, right? So I'll try to cover that. So the first answer is actually the easiest. Can you get R from the Nyquist plot? And the answer is yes. So that's an easy answer, right? So got my pen here. I'm going to make great. We can get R from the Nyquist plot. So if I have a Nyquist plot, so for those who may be familiar here with the Nyquist plot, you have the Z real and the minus Z imaginary. Okay. And so let's say this is the origin, this is 0, 0. And I have some Nyquist plot. Let's just say I have like a semicircle. This is just some charge transfer process. The ohmic drop, which in this case they called, the questioner asked RS. Sometimes people will call it R0 or R naught. Sometimes you see R like with an omega symbol. These are all just names for the same thing. Ohmic drop, IR drop, uncompensated resistance. I'll get to that in a little bit. But basically it's just this distance. So I've talked about this in some of my EIS webinars, but the distance on the x-axis of a Nyquist plot, where the high frequency intercept is, that's the uncompensated ohmic IR drop that's that resistance. So it's very easy. It's actually quite convenient from impedance. That's why impedance is usually the preferred method for getting IR compensation. If you're going to do like IR compensated CVs and things like that, it's obviously quite visually easy to get, and it's the high frequency intercept. Okay, now physically, what's happening here, right? If we think about circuit wise, right, this process here, right, this semicircle might represent some kind of a Randall's element, right? Some kind of a process that has like a double layer capacitance and charge transfer resistance. So these are Faradaic, non-Faradaic processes that are occurring on our electrode. You know, I've got some redox process, A goes to B, and I've got some double layer capacitance building up on the surface. But the uncompensated resistance takes the form of this resistor, right? So this is my series resistance, uncompensated, all the names I keep repeating over and over again here. Okay, so that's this resistor. Okay, so that's what this shows up, and that's what this physically looks like here. Okay, now the parts of this question, so I've said, you know, it can be calculated from Nyquist. What's the reason if I have a high RS value? Okay, so if this distance right here is really big, what are some of the reasons? Well, there's a few reasons, generally speaking. And the first would be if I have my potentiostat and I've got, you know, it's got a cell cable and I've got my leads, and then, you know, it ends in alligator clip here, and then I've got this clip to another long cable with a banana jack, and I got a alligator clip on that. These are great alligator clips, by the way. And then I've got that connected all the way to my 3 electrode cell with my electrodes in it, and I've got all this distance of cabling here. That's a very bad idea. So that's one of the reasons that you're going to get noisy data. You're going to get a lot of extra problems. It'll be really hard to get impedance at all, and you might have a really high ohmic drop. This extra cabling, this extra connect, every time you make a cable connection, all of this kind of stuff. So the advice, generally speaking, is get my potentiostat as close as possible to my electrodes. Reduce this distance as much as you can. You want to, I mean, you have a cell cable, so you have some distance, and you have to physically connect it, but you want to try and reduce that distance as much as you can. Now, apart from that physical kind of thing here with the cabling and everything else, the other reasons that typically cause high ohmic drop on compensated resistance are things like the electrolyte concentration. For typical, you know, aqueous electrolyte, usually you might have something like 10 ohms. You know, if you have a pretty concentrated, you know, half molar sulfuric acid or base, things like that tend to have pretty moderately low impedance for IR drop. Non-aqueous tend to be about an order of magnitude higher. Again, it varies, but non-aqueous electrolyte tends to have a little bit higher of an ohmic drop, and some of the reason is also like some electrolyte isn't quite as conductive. You can't usually dissolve quite as much in some cases, and so it'll be a little bit higher. And so that's another one of the major drivers with a like 3 electrode or 2 electrode systems, you know, liquid phase electrochemistry, what leads to uncompensated resistance, high ohmic drops. Okay, now the last bit is similar to what I just talked about with the answer to Luca's question, was also related to the distance between the working and the reference electrode. And so one really important point to make about this is that this kind of uncompensated resistance is exclusive to 3 electrode electrochemistry. It is not the case with 2 electrodes. So if you recall, Alex, in one of the previous questions, you know, he drew this situation before he talked about, well, we should add a reference electrode, right? He drew this 2 electrode system. Okay, so you had E1 over here and you had E2 over here. When you have a 2 electrode system, you do not have uncompensated resistance. There might be ohmic losses or something like that, but there's no uncompensated resistance. That term right there, just to be clear, uncompensated resistance, refers to the uncompensated resistance between working and reference electrodes. Okay, so in a 2 electrode system, you have oxidation happening here, you have reduction happening here. Essentially, whatever potential and current is occurring on E1, I necessarily have the equal and opposite happening on E2, right? This is just like balancing the equation and everything when I have a 2-electrode system. However, if I have a 3-electrode system, the current will be equal and opposite on my counter electrode, but the potential will not necessarily be equal and opposite. That's the difference when you have a 3-electrode system. You're controlling the potential between my working and my reference. And as a result, the potentiostat has to do whatever it can to the voltage, the potential of my counter electrode to compensate, to get the current that I need, right? And the current will flow between, working and counter, but the voltage of my counter might be whatever it is, okay? And so this is kind of at least the reason of why in a 3-electrode system, the distance between the working and the reference matters so much, because in theory, I want this distance to be as small as possible. I want to measure the potential at my working electrode as accurately as I can. And my reference is a nice stable reference, point. Now they can't touch exactly physically. You can't, touch your reference and your working electrodes. And if you touch two materials together, like the voltage between them is 0 basically, right? So, I mean, it's just that philosophically you want them to be as close as possible together, but there's just stuff in the way, mostly the cabling and the electrolyte between the two, right? And so that is what leads to those ohmic losses that drop. And so when you do like IR compensation with a potentiostat, for example, that's when the potentiostat can essentially like apply a larger than needed voltage, for example, to overcome the loss from those effects. And so that is only needed in a 3-electrode system, and that is a way to sort of overcome that loss from those effects between working and reference electrodes. So I'm gonna leave it there. I think hopefully that kind of answers that question about IR drop and kind of funnels from the other questions that we had as well.
Yeah, that's
another
very good. We have a follow-up question from Luca, actually talking about solution resistance.
Yeah.
And is it still correct to measure OCP in very dilute electrolyte in order to decrease the Debye length and be sensitive, for example, to protein binding? I don't know very much about Debye length, so I'm actually looking at it right now. But when you decrease the electrolyte concentration, the Debye length decreases. I know that the OCP should, I think it would increase at lower, the resistance will be higher.
I think let me show an example. I actually have this leads into, I have some like IR compensation data. So increase in Debye length. Yeah. I guess one of the things that I would say in response to that is like if the reason that you're doing, for example, dilute concentration of electrolyte is because you need to facilitate protein binding, and apparently that is inhibited at higher concentration, I think you can do that. And it isn't just measuring OCP. I mean, if you're asking if you should measure OCP very generally, like, yeah, you should always have a knowledge of your OCP in any experiment, if that's that's a helpful metric, or, something like that. That's just generally good advice probably. But also measuring the uncompensated resistance if you're in a 3-electrode setup. Low electrolyte concentration, for example, can lead to stuff that looks like this. Let me open our software here. So for example, this is a 2 cyclic voltammograms. That's data I've taken previously, but this is like ferrocene with really low concentration electrolyte. You see, I have like a duck shape, but the peaks are like really, really split, and it's like spread out kind of. And then the voltammogram with a normal concentration of supporting electrolyte, I think it's like 50 times higher. It looks nice, right? So this is like what I want to get. This is what I have in dilute electrolyte. Okay. But what you can do is just do IR compensation And I don't have that data in front of me right now, but basically you can basically turn this into this for the most part. And so one of the things I could say is that like, okay, well, if you necessarily have to do like low electrolyte concentration because of Debye length, and I'm with Alex, I don't know a lot about that field of study, to be honest. But let's say you need, well, I have to do low, electrolyte concentration because otherwise I can't get my protein to do what I want it to do or whatever. It shouldn't be a problem if you have a potentiostat that can overcome, the ohmic losses that you're going to have. So in theory, you could still, and then if you do like, like bulk electrolysis or, you're driving some current, it's like, oh, well, I'm going to get, a milliamp, but it should be 1.2 milliamps because I have ohmic loss. So you could just do IR compensation, right? Your potentiostat can overcome the ohmic losses that's like limiting the current you're getting, right? And you could do something like that. So in theory, you should still be able to do this. It's a lot of modern potentiostats. You might have some more context about the Debye length that I don't know.
Yeah, no, I don't have very much. But when it comes to like protein binding, I'm assuming Luca is talking about the protein binding to the electrode surface.
Yeah.
And that perhaps if there's a lot of ions, like double layer in a way, it's going to limit the binding of that protein.
Yeah, and possibly too, like proteins are either larger, physically larger molecules.
Yeah.
So if there's a lot of, I don't know, ionic interference or something like that, that could I don't know, inhibit in some way. I'm also not a protein expert or anything like that.
And electrochemistry.
But speaking of binding, Barry asked a question. How do you like that segue?
Go for it.
Early on about basically was what would be the right DPV, so differential pulse voltammetry, and then saying you're not sure if this is the right experiment, but the settings to measure the binding constants of two species. So I wasn't really familiar with the term binding constant, but anyway, we sort of just did a little bit of research. It seems like binding constant is effectively the inverse of the equilibrium constant. So like if you have some experiment, right? Let's, whatever you have, like A, B dissociates to A plus B, right? Your equilibrium constant, right? It's technically activity, right? But I'm just using concentration as a shorthand here. We recognize it's actually not technically concentration, but I'm ignoring that for now. But basically this is the equilibrium constant, right? And then if whatever we have here, you have exponents, right? So this is the equilibrium constant formula or whatever. And as I understand it, if Barry's still here, I'm not sure, but the binding constant, which I'm not too familiar with, it's just 1 over K EQ. This is the dissociation, right, of AB. And so if I just go the other way, it's binding A and B together. So something like that effectively.
Yeah.
So I mean, essentially the key here, and Alex, you can sort of jump in if I'm going to butcher just from thought. The key is Gibbs free energy. So basically something like, again, I'm going sort of by memory here, but like delta G, like the standard Gibbs free energy is minus RT natural log of K. So which is in your case, I guess would be 1 over K binding. If there's like a binding constant, so you might have K or 1 over K here, whatever it is, right? Okay, perfect. Barry's still here. Appreciate it. So something like this. So, right. So you have this expression linking your binding or equilibrium constant to the Gibbs free energy. And then again, Alex, please correct me here. Delta G0 is, what is it? NF. What is it? NF
E naught.
E naught. So something like that. Yeah. NFE. This is a terrible drawing.
Yeah, maybe minus.
I'm going to draw
NFE.
it better. I feel like my ability to draw is it minus NFE?
Well, I can show you. There's
I don't know something to this effect. I'll finish my thought and then I'll let Alex take over.
Sure, I'll just
effectively something like this is that you're using the Gibbs free energy to equate the two. Okay, so what you're after is E naught, right? The standard potential of whatever reaction you're this AB, whatever. If there's some redox in here, effectively, I mean, right, I'm making some assumptions, but you're after this E naught, and then through that you can equate the delta G to your binding. You could back calculate your binding constant because you know what temperature, the ideal gas constant, the number of electrons, or in theory, Faraday's constant, right? And so DPV, right? DPV is an experiment. You're basically doing something like this. You're doing a pulse with a background and you're subtracting. And what it does is it's subtracting background current constantly.
Yeah.
So that when you have a peak in a CV, for example, it's like where this peak location is also coupled with, like, this is a current response. It's coupled with background processes and double layer capacitance, stuff like that. When you do DPV, you often get something like, it'll clarify where this is terrible drawing. I do apologize. You get like clarified where the peak location is. So effectively what the parameters should be, the answer to that is unfortunately trial and error. I don't have a good answer for you because there's like the width of this part, how high up you go, the time of each pulse, all of that is like, you got to just try stuff like the auto filling, like in our software, for example, you've got, I'll just show you the DPV experiment. I'm not going to run it because it's on a battery. I'll probably destroy my battery, but DPV, for example, you've got like, you might do 50 millivolts with a, 10 millisecond pulse for a total of
0.1 seconds.
Yeah, 100 milliseconds and then increment at 10. So I know this is like a lot, what do these really mean? It makes a waveform that looks something like what I just drew. And then you're measuring at the end of each of those periods of time and it does a subtractive thing. You might just have to test this. Like you might end up doing a few, I don't know, times of trial and error and then finding the peak clarifies itself. And then when you get that E0, you can, in theory, use the equations, right? And sort of back calculate your binding constant or equilibrium constant. Something like that, I think, is the answer to your question as best as I can.
Yeah. I think Barry, let us know if you have any follow-up. Yeah, the only thing I would just share, this is, if you can see, this is just a website, but this is the relationship from general chemistry.
And if
like
it is a
little
minor
triangle
good.
thing.
Okay.
Yeah, so
I got it.
So you want to get K, and it's related to the potential of the cell via this equation. So yeah, all you need to do is when you find E naught, either using CV or DPV or whatever, then you can get your K. 1 over K should give you your binding constant. I think the only thing I would say, let's see. I haven't any other thought. Oh yeah, the only other thing I wanted to mention was that for the equation that Neil showed with just like two things dissociating, there needs to be some electron transfer.
Yeah, I sort of skipped that part.
That's all. It just in that dissociation, there needs to be a reversible electron transfer process. Otherwise, you're not, if there's no electron transfer.
Yeah, if there's no electron transfer, the electrochemistry part of this is like irrelevant, right? Yeah. Or at least makes it harder to get any measurement, right? You're measuring electron transfer with a potentiostat fundamentally. So without that, you're kind of in trouble.
Yeah.
Right.
Now, Luca had a follow-up. This is again talking about like the bi-length and proteins on electrodes. And he said that he doesn't want the double layer, the electrical double layer, to screen the charge of proteins that should change the OCP.
Yeah. So it was kind of what you said, right? It was that the double layer might have an impact on the protein. So I think that's it seems like Luca's confirming what you sort of thought. Yeah. And that is,
there may be no way to get around the double layer. Like
there is no way to get around the double layer. I mean, like if you use pure water and there's no electrolyte at all, you don't have electrochemistry. You can't do, right? You have to have some electrolyte. And if you have some electrolyte, you're going to have a double layer.
Yeah.
There's no way around it in some respect. I would say, right? Like,
I think you will find like there may be trace contamination of something in your water that's gonna it'll be ionic, because so like ultra pure water, it's like 18.2 or 6 mega ohms or something. If you get one of those ultra pure,
well, I used to use those when I was in graduate school, the millipore or whatever it is there. I'm not trying to give any free marketing to anybody here, I guess, but
Well,
it's-
yeah,
like 18.2 mega ohms, it was a Siemens. It's
yeah,
been a while. I work at a company. I don't have to do research anymore. Okay. Don't make me think about these things. I don't have to think about, but the resistance and theory of pure water is whatever. But
Yeah.
yeah, like you're going to have some amount of electrolyte.
yeah.
And
And you may have like just CO2. Like you may have ions just because there's protons and some OH, and that will the surfaces are weird and complicated, especially in
very much
solution.
are.
So
Here's as well, just as a
Mhm.
quick diversion, to answer the DPV. This is what the DPV waveform looks like. To just as a, this is a knowledge base article on our website.
Oh yeah.
So
that's very good.
there's different forms of pulse techniques that I just wanted to point out. Basically, you're incrementing the bottom part and the top part. That's what that increment is, 10 millivolts. So this is like 10 millivolts. And then there's versions where you keep the baseline the same and increment this. And there's normal pulse, which is similar to this, but DPV, it's like this is a longer section. You can see how like the bottom part is longer. So there's different pulse techniques. So DPV isn't the only one you can use. I just kind of wanted to mention that. You could use DPV is one option. There's normal pulse. There's what is it? There's normal pulse, differential pulse, and square wave. Square wave is pretty common. Square wave is a useful technique as well. So I just wanted to kind of throw that out there.
Yeah. So Barry's asking about is there a resolution limit, differences in potential in DPV?
Resolution limit.
It's based on the voltage range.
Okay, so yeah, the exchange between the two is slower than the
Yeah.
redox. Are you talking about resolution and difference of potential? Yeah. Yes, of course there is. I mean, and probably that's more intricately tied to
Potentiostat settings.
the potentiostat itself, right? So it's like, like a typical potentiostat that can do this kind of thing might have potential, like the lowest DAC count. It's like microvolts, right? It's like, it depends on the voltage range.
It depends on the voltage range.
If you have like a 2.5 voltage, like some of our potentiostats have like a 2.5 volt range. I think that I could just look it up, but I think that the limit, the lowest DAC count measurement of that is, hang on, I'll get it for you. It is here, filibuster for me. I'll get it.
Oh, it's
78 microvolts.
78.
Yeah, okay.
78 microvolts.
I had it very quickly here. So I had it very slow.
Depending on what potentiostat you're using, and the ADC, the A to C converter on that is going to limit the voltage.
So in some sense, that's kind of the answer, right? It's like it ends up being in that range of like, let's say tens to hundreds of microvolts of the limitation or whatever. So
wave driver 20.
Oh, wave driver 20. Well, there's
all right. Well, there you have it.
That's directly the answer.
Actually, then that's exactly
basically the mathematics is it's I mean, you could do this. It's 2 to the 16 power, which is about, what's it, 65,000?
Yeah, 65,000.
And it's 2.5 volts. It's bipolar. So it's 5 total volts. So a quick back of the envelope calculation is you take 5 volts divided by 65,000.
Yeah.
What am I doing here? 5 over 65,000. And you end up with, multiply by 1,000,000.
Yeah.
It's 76.92 if you do the math. So it's about 80, give or take 78. Yeah. So that's how you get that number.
Yeah. There's like some N-1 level thing when you do it. It's like,
But technically you get all that kind of stuff, but that's the answer. So it's like, if you're doing it in that limitation, and now you might find when you're using your wave driver in Aftermath, there's other software limitations or just stuff built in. Like if 70 microvolts is the limit, you want to do 70 microvolt intervals. It probably isn't possible. There's other stuff that is hard to anticipate, I suppose, from a user's perspective, but like you can only probably do like practically like in the software, you might only be able to type like 1 millivolt or half a millivolt, or I don't know, it won't allow you to go lower than a certain amount, I think, because there's also the measurement of the perspective current, right? It's like, it's not, you're going to have some limitation there too, right?
Yeah. So when you're doing DPV and you're applying a potential, the applied, so we don't care about what the current's doing, but if we apply a potential and set the range, and then you're right, there's a speed at with how quickly do you measure the potential.
Yeah, that's the other
especially
thing
with the timing that you're using of the pulses, which
Hmm.
I think should be slow. Like if you're using the parameters Neil had, like 0.01 or I think 0.003 seconds was the
Yeah,
pre
3
and post
milliseconds.
with
You're getting,
sampling time.
yeah,
Yeah, you'll definitely get
because
within
that's the other
3 millivolts.
resolution limit you're going to run into as you start trying to decrease these parameters really, really down, is the
Yeah.
time limitation of the instrument. And it's about 100 microseconds.
Yeah.
Something like that. So it's like you're going to eventually reach a point where like it can't measure
Mhm.
fast enough you're, and then the other part is that it's going to take you absolutely forever if you're stepping up like 100 microvolts at a time, right? Like your
Yeah,
the effective scan rate of a pulse, it's like the increment over the period or something, like if
you're going like a volt range.
yeah,
like,
you're going,
it'll
it's
take
going
a
to
long
take you absolutely forever to get there. So that's the other part to think about. I mean, if you spend less time at each because you're doing such small steps, you're encompassing a lot of potentials to try and help your resolution problem. But then you can't spend very long at each of them because it'll take forever to get there. You can't spend like 10 seconds every 100 microvolts. You'll be there forever for it to move a millivolt, right? I mean, it's right, like at some point, the timing just makes your life absolutely miserable.
Yeah, I hope this is clear, Barry.
Yeah,
Like,
something.
kind of-
So, I mean, ultimately, again, I think that the unsatisfying answer is a lot of this is trial and error from the parameters perspective.
Yeah.
But in theory, what Alex showed with like the triangle, effectively, you should be able to hopefully clarify the E0 through some trial and error, and then use that to get an estimate of your binding constant. I think that should be possible.
Yeah. I think that's good. So George has a question. He just showed up. Good old George. All right. Very good. So Barry thinks that this is
Okay.
good.
Yeah, I
a
hope
good
that was
place to
helpful.
start, at least for now. And we'll have more. Hopefully, we'll have more of these live stream Q&A, so people he can come back later with next follow-up.
Yeah, George asked about EIS parameters here. It looks like.
Yeah, he was talking about what parameters you would use for EIS if you had steel with a protective coating on it. And
Yeah,
that was
so
600 microns in thickness.
So I think this, and I know maybe if you didn't join for some of the whole live stream, George, I talked about one of the questions that I answered previously was about someone was asking like, what is the lowest current you can accurately measure with impedance? So your question is actually kind of related to that from the perspective that a thick coating, like a protective, often anti-corrosion coating on steel, will elicit a very high impedance. And because it has a high impedance, it's probably going to have a very low current response. Okay, so, I mean, you have two options here, right? You can do potentiostatic or galvanostatic. Most of the time people do potentiostatic impedance here, but you're going to be severely up against the capabilities of your potentiostat. So, it depends on how protective the coating is. 600 micron is pretty thick.
Yeah.
So I do suspect that from a protect my material perspective, that's great. From a get good data perspective, it's bad.
Yeah.
Like you need a potentiostat that can measure gigaohm or teraohm levels of impedance, probably, if you have something like that. And because it's probably mostly capacitive, you have a situation where it is just the impedance is getting just larger as your frequency drops. So you might not be able to, it depends. I mean, maybe not. I don't know. I've seen corrosion stuff where you get inductive loops and you get, some of these things Alex loves. And, sometimes you get Randall's elements, you get a charge transfer process, but sometimes you just get this capacitive kind of thing that is crazy and maybe hard to figure out what's going on. And when that happens, it's like the impedance is just getting bigger and bigger and bigger as the frequency drops. And as the impedance gets bigger and bigger and bigger, the current response just goes down. by orders of magnitude. And so eventually you're going to hit that limit where your low frequency data is just going to be garbage, because it's like trying to measure picoamps of response. Like you put in a, millivolt and you get a nanoamp, or whatever, so it's like, it's just a mess. So, to some extent, the answer to your question about what parameters should you use, big amplitude.
Yeah.
Like
very big amplitude.
Big amplitude, right? You're going to run up against that problem. It's like your inclination is to do 5 millivolts or 10 millivolts peak amplitude. Well, if you do that, you don't get anything. So maybe you got to do 50. I mean, that's tricky, right? It's like the higher amplitude, it might not be linear, or you might be corroding it more. I don't know. You're going to be doing something more aggressive to your system, but you might have to do that because if the impedance is so large with a really thick coating, you might have to do a really big amplitude to get any data at all. And so don't be afraid to play with the amplitude of your impedance experiment, make it a larger, you can step it up incrementally. Like you could do like 10, 20, 30, 40. You don't have to go to like right to a volt, something crazy, but you might need to, you're already using 50 millivolt amplitude.
Yeah. So what's the data looking like?
I mean, the question is, what does your data look like, right? If it's still really noisy, you might have to increase it more, and just check Kramer's Kronig to make sure it's not unstable, non-linear, all that kind of stuff. But yeah, and then, you can try galvanostatic impedance, because if the problem is you're not sure if you're in the linear region, well, do Kramer's Kronig. That's how you can at least get a decent estimate of that, if you're linear or not, right? If you can view the Lissajous plots, you can get a visual estimation of if it looks linear or not. Mm-hmm. And then Kramer's Kronig analysis on the data afterwards will be some indication of if it was, adequate EIS data for analysis purposes. So there's that. And then you can try galvanostatic impedance, but because let's just say it this way. If your amplitude is in this, whatever range, and it's not linear, or the problem is that you have such a high impedance that your current response is so small that your data is poor, and you want to do galvanostatic impedance to guarantee you have a certain current response, to guarantee you get a result, you might run into the situation where now, as you drop frequency, galvanostatic mode, you're going to start doing, okay, well, I definitely want like a microamp of current or a milliamp of current, whatever it is. Now your voltage swing is going to start getting crazy. So you don't want to probably be in a situation where you're swinging the voltage, the potential response from your galvanostatic is like 700 millivolts or like 1.5 volts up and down. That's a lot. Like that's a fast CV. You might damage something. You might corrode it really badly. So you can try galvanostatic impedance, but keep your finger on the cancel button ready to go, and watch if again, that depends what potentiostat you're using. You said you're doing 8 decades of frequency. That's fine, but going down to 10 millihertz,
that takes a lot.
That's when it starts getting high impedance usually, right? Maybe not, maybe I'd have to see what your data looks like, if it curls, if it doesn't, whatever. But as your impedance grows, if you're doing, you can try sometimes galvanostatic control works a little better for a potentiostat. It just does. And maybe you'll find that works. You can try that. But again, you might've missed part of the answer I did earlier with this, but part of the suggestion for galvanostatic mode is to like pick an amplitude that's small, that you think might be small, and then ramp it up slowly. Same way as, for potentiostatic. But if you're doing galvanostatic, because of the risk of having the voltage swinging so crazy, start with like a very small current amplitude. Watch it. And you might get total noise right away. Like if you just do like a microamp and it doesn't do anything at all, or you do a nanoamp, or I don't know, whatever your resolution of your potentiostat is, right? You might get nothing at all. You might get just total noise. Fine. Better to get noise and then increase it than to start too high and damage your system. And then, well, then you're in trouble, right?
Yeah. Neil's the EIS expert. I mean, I think that's
yeah, I mean, that's my general advice for that. But
we also don't know what it looks like.
Yeah, I mean, some of that is is a bit of a tricky if depending on what your data looks like specifically, you know. And
he couldn't do like I know CV probably wouldn't work, but right, like to determine if something's linear, it's like if it's in the range in the CV and it looks small, then
you can do CV. I mean, and that, you know, that in the absence of an EIS capable potentiostat, right, you can, the other way to get like it's like a conductivity measurement, right? You know, in some capacity, but you can do like measure OCP. I mean, this is LPR, right? The linear polarization resistance is a way to measure
that's also true.
resistance with a DC. It's the primary way people measure corrosion resistance it's a DC method. You just start at OCP and you just do a very small sweep, you know, plus or minus 10 millivolts from OCP.
Yeah.
So you can do a CV, like a slow scan CV, you know, basically around the open circuit potential, and that will also give you an estimate of the measurement. But impedance is different because it's fundamentally you're changing the frequency and all that kind of stuff, you know, so it's a little bit different. It'd be like doing CV like at 1 millivolt per second and then 10 millivolts per second and then, you know, whatever, something like that.
I think that's all the questions.
That's all we got basically. Yeah, we'll wrap it up here unless there are any other questions. I know there's there's sort of a, you know, a bit of a delay, I guess. Between when I say this and you hear it. So, but we can probably the thing, I don't have access to the steel, and that's why I'm using magnetic self cells. I don't know what that means.
Yeah, those kind of like magnets on the cells that slap together.
Oh, something like that. Yeah, I don't know what that does to the electrochemistry. It's interesting.
Yeah, try to keep magnetic stuff away from your electrochemical cell.
Yeah,
generally speaking.
Yeah, electromagnetism, right? If you have a magnetic field, it induces a current and vice versa. So some of those things can impact. It depends. I mean, especially if you have small currents, it's like, gosh, if you have small current, a moderate magnetic field could induce current to interfere with it, right? So in theory, I think it could be tricky at the very least, but so okay, I guess we'll wrap things up here. You know, again, I'll just wanted to thank everybody for watching, whether you're joining us live or you're watching this afterwards. This video will be on our YouTube channel. You know, for if anyone wants to watch or review some of the questions and the answers that we've had here and comment on the video, and we'll keep the live streams coming. We'll do more of these as they're, you know, as the engagement is good. We're happy to do these, and hopefully it's been helpful for